start. So hi, I'm Lim, and today's topic is effective Markovian dynamics method for solving non-Markovian dynamics of stochastic general expression. Let's start with reading out today. You all have the abstract. So, what is the job sentence?
Second one.
Yes, I think so too. So, this second one could be the gap sentence. And how do you think about this abstract? Really? How do you think?
I think it's a very standard abstract. Small background and then the gap, and then you mention it's
How about Kangmin? Kangmin? Oh.
For me,
So actually,
but I'm sorry for interrupting. But before this, how's his talk compared to last week? I know everyone in this room was in his genre club last week, right? Who was it last week? Hands up. Please. Who was in his talk last week? Okay. And compared, what do you think?
Better understanding.
You understand it? What about me?
clear due to the step-by-step explanation.
Then let's be frank. Last week Friday, how many people understand what he taught about the his presentation about it? Understand? Okay, one. Okay, what about today? How many people understand it? Okay, good. So yeah. But anyway, why I suggest he do the duplicate presentation is it's a good example. So next time when you present the general club, thinking about compare his prior one and you one. Okay, but if you go to the conference, 90% present the work in the first way. Okay, there are only few people who can present as he did today. It's not easy. Okay, so please memorize it. Got it? Okay.
so actually this sentence and the following sentence explains all about this manuscript. So my talk today is focused only on these two sentences. General expression models, blah blah blah. Notoriously difficult, and they develop some alternative method. So let's start with what do you mean by non-Markovian system? So in many biological systems, there is some multiple step. So for the protein degradation, first one ubiquitin detached to the protein, and after that, the proteasome detect this protein with ubiquitin, and they finally degrade it. But this multi-step is complex. So for mathematician's perspective, we just simplify it by proteinase degradation will be degraded after some delay. Similarly, after people infected by disease, there is some multiple steps, such as virus replication in your body and immune reaction, and you finally become infectious. It means you can spread the disease to other people. But because this is too complex, mathematicians just simplify it by just incorporating the delay in this model. So for the protein dynamics, we have this kind of simple model which protein is produced with identical rate, and after some delay, they are being degraded. Then for this model, if we wanna track the protein number as a time course, then there will be the first protein which will produce, and it will degrade it after some time. And for second protein, it will also degrade it after a certain time, and third protein, and so on. Then if you have the timing of these events, I mean, if you have the timing of when this first protein is being produced, and when this first protein, second protein, and third protein is disappeared, then what you can do is you can track the protein number, like total protein number in the system as a time course. An important thing here is that this delay, I mean the time interval between one protein is created and degraded, is not same for all proteins. It is different for all proteins. So rather than it is fixed in one certain value, it has some distribution of this. So depending on this distribution, each time we simulate this system, or each time we observe this system, this protein pathway will be different. So if we take a snapshot of the protein number, such as time 10 seconds or time 20 seconds, then rather than protein number is fixed at one value, it has something like distribution of the protein number. So by if we define different distribution for this delay, I mean this time interval, this distribution of protein number will be also different. So, and to model this kind of system, previously one most common approach is just assuming the exponential distribution. So this exponential distribution means that you have the highest probability of having a shorter length of delay, and you have some less probability of longer length of delay. Then why mathematicians use this exponential distribution is that if you once assume this exponential distribution, your mathematical modeling becomes really simple. So it means that, so to what that means, let's see this example. So what we want to do is we are in the time t, and what we want to do is we want to find how this system will be changed. I mean, how the protein number will be changed after this time t. then that change is depending on this red length, because this determines the event first after this time t. Then the system, how the system will work will depending on the distribution of this length. Then what will be the distribution of this length? So to intuitively think what will be this distribution of this length, let's think this way. So you have this exponential distribution. Then let's say this protein one, before time t, they already spent their 10 seconds of their lifetime. Then the remaining this length will follow the distribution here, which is this exponential distribution after the 10 seconds. And for the second protein, it will have a distribution like this, like starting from distribution after the time 6 seconds. And for the third protein, it will have distribution after the 3 seconds. Then if you see this one, they look all similar. In particular, they look similar to the exponential. Then are they all exponential? So my answer is yes, and you can actually prove it mathematically. And if you are interested in mathematical proof, you can see the appendix in my slide. And yes, so because important thing here is that because this both this blue line and red line has same distribution. How the protein number will be changed does not depending on this 10, 6, or 3. It is just exponential. So we call it as a Markovian property or Langevin property, which means that this red length does not depending on how much you spend. I mean, this red length does not depend on the history. So we call it Markovian property or Langevin property.
So one comment is, let's look at the V3. Of course, they are not equal. Why they are not equal? Sizes are different, so they are not the same. But what we have to think about is, we know that this up to 10 nothing is happening. So that if we give that condition, we should change this to the probability distribution with the underlying area should be 1. So we can increasing the height a little bit. For instance, here area is 0.5. So what we have to do, we multiply everything by 2, then it will be 1, right? So then let's scale up. Then what do you think? They will be the same or not? They will be the same. But that's only true for exponential distribution. But if you bring the gamma distribution, let's cut this part, this part, this part. If you scale up, shape will be different. Okay? 내가 한 것만?
네.
Okay.
So yes, because it does not depend on history. It means that we don't need to incorporate history in our model, which simplify our model. So really great, but is it real?
Realistic.
But no, actually no. So for the protein degradation, distribution of the weight, yes, most of them are like exponential. But there is some portion is like green or blue version. The 10% of proteins are degraded with non-exponential delay. And for the infectious disease spread, this latent period and the time interval between exposure and the infectiousness does not follow exponential. As you can see in this graph, it is totally different from the exponential distribution. It is actually well fitted with gamma distribution. So it means that exponential distribution is just fantasy. It is not realistic. Then, if we change this distribution of the blue line as a gamma distribution or other non-exponential distribution, some tragedy happens. So, for the first protein, the remaining we already spent 10 seconds. So the remaining distribution is this. And for second protein, remaining distribution is this. And for third, this. So as you can see, they are all different. It means that we have to check or we have to consider all the proteins here, and we have to incorporate their history into our model. So it really complicates or make our model really complex. So for example, for the infectious disease model, compared to the left side, which is Markovian model, if we see the non-Markovian model, it is much more complex because of it should incorporate the history of the exposure history. So what this paper wanted to do is we want to solve this one, this right one, but we will somehow use this left one to solve this right one. So to understand what they did, let's come back to a more simple example. We came back to this simple example of protein production and protein production index. And then for this system, let's assume that there are 5 proteins were created, and what we want to know is protein number, more precisely distribution of the protein number at time t. Then let's think, to make it simple, let's think what is important to determine this protein number at time t. First, this protein 2 and 3, they are already gone, so let's ignore this. And for the future degradation of protein 1, 4, 5, it is future, so let's ignore this because we only care about the protein number at time t. Then, when we create or when we imagine a new world, only with protein 1, 4, 5, then there is only this first reaction. So in here, we have new important thing here is that if we create a new word, we can delete one reaction, which is the source of non-Markovian property of the system. And then important thing here is that even though we created a new word, if we at time t, these two words have the same protein number, because this new word will count the protein number at time s, which were still alive at time t. And if we change this to time t, then it will be number of proteins at time t that will alive until time t. It is just number of protein at time t. So it means that at time t, this original world, original system, and this new system have the same protein number. So strategy here is that rather than solving this system, we first solving this system and plug in the t to this system. Remaining question is that, of course, even we know that there is only one reaction, but we don't know the rate of this reaction, what rate it has to be. So remaining question is this rate, and for this rate, it is quite simple.
So, so right side, no degradation. Always increasing.
Yes. I mean, always increasing until t.
Then we don't care.
Yes, after t we don't care. Because what we want to do is we want to find the number of proteins at time t. So after time t, we don't care.
So PST definition is can you just explain what would be the meaning of P2 semicolon 3?
2 semicolons, right? So if we so this means that.
Or can you use that data slide example? How PST looks like?
So PST is the stochastic process, which have the timeline from this 0 second to the t, and the PST will evolve like this. At this time, it will become 1, and between this, it's still 1, and until this small time interval, it will become 2, and before time t, it is 3.
Everyone understand what the PS of t. So we look at the time equal s, then we will count the protein number, how many of them will be still in the time equal t. Initially 1, then 2, and then equal 2. Right? Okay.
Is that from active to protein that we are will you assume that is the plasmid process that
Yes.
but in the right side you don't know what is that it would be if we define the P of S.
So to determine this rate, it is simple. So we want to determine the rate at time s. Then it means that the U protein at time s So first of all, because the original creation is the rate k, and what we also want what we also want to what we also have to consider is that this new protein should survive until t, and the probability is this. I mean, their degradation delay should be longer than this time interval, so that they can survive until time t. So we have to multiply the probability of degradation delay is longer than t minus s. So but this new system is the system with only the first reaction with this rate.
Can you explain that example again? How this?
So this rate means that rate at s time s. Then let's think that at time s there is
Usually s equals to 0, right? And the number of one locations.
No. So this so what I wanna determine is the rate of the production of protein at time s.
Time s can be anything.
Yes,
So let's think about s equal to 0.
s equal to the 0. Then it can because the protein can be produced with rate k. We can think that there is really shorten their k proteins there, and because time 0 to account for this PST, they have to survive until time t. Because the definition of this PST is the number of proteins that's still alive until time t. So at s equals 0, this K proteins is created, but they have to survive until time t.
So here, what is the tau? Tau is the time delay. I see. Okay.
So I think it's like, so we have one passing process making protein, and
Yeah.
we are just dividing that process with two processes. And one process is,
Survive.
yes, yeah, put it
After
until, right,
t and
and then rise with time. In that way, we can
Makes sense. So, for instance, in this example, okay, so everyone okay? I think this is a really key idea of this paper. Everyone is okay about that rate. So, effective production rate is original production rate times certain probability that protein is surviving for greater than t minus s. Because if we want to observe the protein at time equal to t, that protein should be produced and survive until time t. So everyone is okay about this equation? If you don't get this one, later part will be nothing left to do, right? Please think what that means. So let's do this example. With this empirical data, if our S is here, what is the probability? Actually, yeah, if we have a distribution, it's wrong, but let's do with this simple example. So here, among the three, how many are survived? Or during this time? All of them are survived. So that this will be 1. It's wrong, okay? Because actually it's a fixed one, but that's with this example. But now let's look at here. Let's look at here. Among the 5, how many survived? Only 3. So then when we actually effective production rate, we can take that k times 3/5. But this, with this example, but actually this tau probability we already know there is time delay. Right? Time delay distribution, using that we can calculate it. Does it make sense? For instance, t minus x, for instance, s equal to the t. So s equal to the t. Just here. Then t minus t equals 0. Right? Tau is greater than 0, probability is 1. It should be 1. That's the original production rate, because observing time and production time are same. There is nothing to lose, right? Correct? But if t minus s become larger, this gap become larger and larger, this probability become what? Smaller and smaller, because, does it make sense? Or do you want a more practical example? Let's say, yeah?
Suppose one protein degradation is between the S and T. Look at the 1 and 2 and 3. So between 3 and 4, there is a gap. Okay. Suppose another protein degrading between that time. So what will be the equation and what will be the understanding?
Yeah. Or maybe you can think in this way. Every year, 30 graduate students come to the chemistry math department. So the rate is 30. Okay? So all of them succeed? Or not? So as this becomes longer and longer, the survival rate is decreasing, right? So the effective production rate is changing. Anyway, yeah, think about it. I think this is a clever idea. And that?
So I think that's this is all. Actually,
Is that all?
Yes, it's all. So
Yeah.
the important thing here is that is this system Markovian? So yes, because their evolving of the system only depends on S. They don't need any like previous history information for the evolution of this dynamics. So they are Markovian. So we can expect that it is simpler to solve. So we will call this as an effective Markovian dynamics, EMD.
S is current.
S
S is current. What is S and T difference? The meaning. Time for S, time for T is the future observation and S is current.
No, T is the like time of yes. So if you mean current as what we want to know, then time t is the correct.
But what we want to know I call future.
Then t is future. So t is what we want to know, and s is then correct.
Correct. And then if we know it, that means we don't need the information before the current time s. That's what is one called.
So actually, this dynamics, it is really easy to do. Actually, you can derive the protein number distribution in this form. And if you want to look details how to derive this, then I wrote details in appendix, so you can see this. See that? So important thing here is that from this non-Markovian system, we can derive the effective Markovian dynamics in some way, so that we can solve it more simply. That is the key. So actually, it can be applied to other methods. So it looks similar, but it also has the mRNA between this protein. Then if this protein have non-exponential delay, previously some studies wanted to solve this, but they actually solve it under some condition. They assume something. But by using effective Markovian dynamics, then we can delete this non-exponential delay, and we can create the effective Markovian system with this. So if we actually solve the protein number distribution from this effective Markovian system and compare it with the stochastic simulation results of this non-Markovian system, then result will also look like this. So here, this gray area is the result from the stochastic simulation, and the blue one is effective Markovian system, and this red one is this previous study. As you can see, this blue one is really the same with stochastic simulation, but the previous one, which assumed some conditions, it is really different in accuracy.
Although it looks very simple idea, believe or not, left the top. People have to try to serve for last 2 decades. Seriously. It was a big problem in the chemistry and biology. But it was a very simple idea. Wow. Just change the, eliminate the decay rate and then incorporate to the burst time, burst rate. Oh my God. As far as I know, there are a couple labs who spend whole career to solve the laptop problem. Seriously. Well, that idea is not that surprising. Okay. Good.
So that's all.
That's all. Yeah,
So-
nature came up. This.
Yeah. So to summarize, by looking at some harsher process of the non-Markovian system, we can derive the effective Markovian dynamics, so that we can use it to solve the non-Markovian system.
이틀 전에 보고 있어요.
전을 원래 가고 있어?
아이브.
누가 전화야?
첸지아라고.
네, 첸지아.
가보자.
제가 이거 라모 그리면 안 돼요.
네, 맞아요.
박경배 친구. 아, 진짜 천재라도 진짜 천재네.
작년에 한국에 왔습니다.
왜 왔어?
쌤이야.
네.
너 만나봤어?
네, 저랑 같은 세션에서.
아 진짜? 얘 어떻더너? 사람은?
되게 또 제가 따로 컨택해서 저한테 질문도 했었고 그래서 컨택했는데 그래서 잘 알려주셨어요.
아, 이 친구 승리했으니까 내가 해야 되는데.
네?
훌륭하구나.
예.
PRL. 둘이 한 거구나.